Hello and welcome to the second video of the FP1 chapter, Numerical Solutions of Equations. On the screen is a starter to review the idea we had in the previous video and to show you something new, and then we'll get into the rest of the video. So if you've got time, pause the video now and give this a go. The question says choose a suitable interval to verify that the function this, which we had in the previous video, has a root at this correct to 3 decimal places. Now we're doing something slightly new here because we didn't go through an example where you had to choose your interval, but we are using the idea of a change of sign. So the suitable interval here, in order to show that this is true correct to 3 decimal places, we should look at the bounds to 3 decimal places of this. The lower bound 0.8925 and the upper bound 0.8935. And if we can show that there is a root between these two, then we have verified that 0.893 to 3 decimal places is a root of this equation. So all we need to do is show that there's a change of sign when you evaluate f at 0.8925 and the function at 0.8935. And if there's a change of sign, then we have done what they requested. And if you put that on your calculator, for 0.8925, you get a very small number. It's 1.51 ... times 10 to the minus 3. And if you put 0.8935 into the function on your calculator, you will get an even smaller negative number, 2.59 ... times 10 to the minus 5. So we've shown that the function at 0.8925 is positive, and the function at 0.8935 is negative, so there's a change of sign. So x does indeed lie between these two values. Which in turn tells us that x is 0.893 correct to 3 decimal places. And there we go. So in this video we're going to look at the first method to find a root to the required accuracy. And this first one is called interval bisection. The idea is very simple. Once we know an interval contains a root, we can make a smaller interval for the root by considering what happens at the midpoint of that original interval. So we're still using the change of sign idea. And here we're saying, basically, if I know from 0 to 2 there's a root in there because there's a change of sign, then I choose the midpoint, a 1, and see what happens. And in this case 1 will give you a positive answer. So from 1 to 2 there's still a change of sign. So instead of from 0 to 2, I have improved the accuracy. I can now say from 1 to 2 the root is in this interval. And then you take 1.5 and you find that the answer is a negative, so to keep a change of sign you're going from 1 to 1.5. And there's still a change of sign when you evaluate the function at these two, so the root is inside this interval. And slowly you can see that your interval gets better and better, and eventually you get whatever accuracy you need. And this is called interval bisection. The idea is fairly straightforward, but there are a lot of numbers involved, so many people, and I think the textbook as well, suggest that you use a table to keep all of your numbers in their right places. So we've got an example here. Use interval bisection to find the positive root of square root of 11 to 1 decimal place. Now for a question like this, it hasn't actually given us a function. So first of all, let's say x is equal to the square root of 11, therefore x squared is equal to 11, therefore x squared minus 11 equals 0, so let's call this our function. And we're trying to find the root of this function. We should use a bit of common sense here. We know the square root of 9 is 3, and we know the square root of 16 is 4, so it's reasonable to start with the interval from 3 to 4. So a table might look something like this. Let's say a is the lower boundary of the interval, 3. We're going to evaluate the function at a. When we put 3 into this, we get 9 minus 11, it's minus 2. Then we've got the upper end of the interval, 4. And when we put 4 into this, we get 16 minus 11, which is 5. So then we want to take the midpoint. So we do a plus b divided by 2, in this case 3.5, and then evaluate the function at this point, which in this case gives us 1.25. So now we ask ourselves, which of our two endpoints do we replace with this? Well, if we've got a negative value here and a positive value here, to keep a change of sign, we need to replace this one, because this is also positive. So instead of using a 4 to get the positive answer 5, we're going to replace that with 3.5 to get the positive answer 1.25. Because, like I keep saying, we still need that change of sign. Now we try it again. The new midpoint of the interval from 3 to 3.5 is 3.25. And the answer that gives us, if we put that into the function, is minus 0.4375. So again, we need to ask ourselves, to keep the change of sign, which one do we replace? In this case, we need to replace the negative one here. So instead of 3, we're going to use 3.25, and you can see that we're making the interval smaller and smaller. And we keep going. The midpoint now is 3.375. And in the function, that gives us 0.390625. Positive answer replaces the positive end of our ever-shortening interval. So we're replacing 3.5 with 3.375. The next midpoint is 3.3125, which gives us a very small negative answer, minus 0.027 ... So we replace 3.25 with 3.3125. And it's not quite obvious that 3.3 is our answer to one decimal place. It could still be 3.4. So I'm going to do just one more. And that will give us 3.34375 with a positive answer, which is enough to tell us for sure that the interval lies between this number here, which gives us a negative answer, and this number here, which gives us a positive answer. Therefore, it must be 3.3 to one decimal place. And you can see one of the downsides of this method is that it can be quite long if you are strictly taking the midpoints. Arguably, once you get to something like this, you would then just start testing 3.35, 3.45 and so on in order to get the answer that you want. But we're sticking to bisection. The second and final example is not quite so long. The equation this has a root in the interval this. Using the endpoints of this interval, find by interval bisection a first and second approximation. So the question here is specifically telling us just do this twice. So if we've got 2 to 3, if you'll excuse my poor table drawing, then we've got 2 here and a 3 here, and then if we put these values into the function, this one gives us a minus 1 and this one gives us a 2. The midpoint, 2.5, gives us a small positive answer. So we're going to replace b with 2.5 and do the same thing again for the second and final time, which gives us a midpoint of 2.25 and an answer in the equation of minus 0.49, a negative answer. So this time we're going to replace our a from 2 to 2.25. And we can say with confidence that the root is between 2.5 and 2.25. Obviously the repetitive nature of the method here makes it a little bit tedious to draw out a table like this, but at the same time this can keep all of your numbers nice and organized so you don't get confused. If you decide not to use a table, make sure that when you're setting out your work, an examiner can follow what you've done. And that should be enough now to practice questions from exercise 3b on interval bisection, and maybe I'll see you in the next video for linear interpolation.